In this video, we're going to look at the area bounded by a polar curve. So, first off, the formula is going to be area is equal to 1/2 integral from the starting angle to the ending angle of r of theta squared d theta. Now the reason behind this is the following. If we consider a circle, so as we look at a smaller and smaller portion of a polar curve, it might look very much like a circle, and take a slice from that circle. The area of this sector, the sector area, in terms of radians will be theta divided by 2 pi times the area of the whole circle, which is pi r squared. Doing a little bit of algebra, I see that I cancel out the pi's, which is why there's no pi in this, and I'm left with theta r squared over 2. Now, in here, if I have some curve that is not a circle, let's just say this is what r of theta equals theta looks like. So it's going to look like a spiral that's going out at a linear rate. Then I need to get a smaller and smaller part to approximate this area as not a rectangle like we saw with regular Cartesian functions, but as a very small sector. So instead of having a theta, I'm going to decrease the angle to the infinitesimal and get a d theta. Since the radius is changing, I have the radius function squared, and I integrate that from wherever I'm starting to wherever I'm stopping. Now, this over 2 is a constant, so I bring the 1/2 out front. Before I go into a couple examples, the biggest issues I see with my students are people that forget the 1/2 or try to stick a pi in here. The pi actually comes in if I go all the way around with the angle, because all the way around a circle or one time around the plane is 2 pi, and so the 1/2 and the 2 pi bring a pi into this. Okay, let's see two examples. Find the area bounded by this. Well, in here, so I know what this looks like. Cosine is bounded between -1 and 1. So 2 plus cosine is bounded from 2 minus 1, 1, to 2 plus 1, 3. And so what's going to happen, now I do have it graphed, but it's going to start somewhere. Let's see, cosine of 0 starts at 1, so it's going to start out, and it's going to basically go in and out, and make a nice little flowery shaped graph like that. In order to get this whole area all the way around, that means that my alpha is going to be 0, and my beta is going to be 2 pi to go all the way around this shape once. So the area will equal the integral from 0 to 2 pi with a 1/2 out front, and I have r of theta, so 2 plus cosine 6 theta squared d theta. Now, I could use even powers of cosine rule to evaluate this, but generally we can just type in the calculator, get a decimal approximation very quickly. That's what I'm going to do. If you do want to see how to take the antiderivative of cosine squared, I do have a video up on that from a month or so ago. But let's go and see how to do this. So make sure I am in radians. I am. And I'm just going to do not matrix, the integral of this function. So I have 2 plus cosine of 6. And I'll just put in an x close that function off, squared dx from 0 to 2 pi. And now this is just the integral part. Something else that people sometimes forget is there is this 1/2 here. So once this evaluates, which might take a little bit of time, I'm going to divide this answer by 2, and I'll get 14.137. So it's approximately 14.137. Just for point of reference, this is what that graph looks like. So you can see starting out at 3 and going into 1, and has this pretty daisy looking type of graph. Okay, one more example, a little bit more difficult. And there are two options here. I want to find the area of one petal of this graph. And the two options are this. I can either find the entire area and then divide by the number of petals, or I can find theta for the start and stop of one petal. Now, most of my students prefer this method. It's pretty straightforward. There is one trick to this. In order for this to cycle back around, because of the way that sine is periodic and this horizontal shrink works, this area for the entire graph is only going to be from 0 up to pi. But once you catch that, then it's just sine squared 5 theta d theta. And that's for the whole area, so I go to the calculator, clear that off, and I'll put in the 1/2 to start with. 1/2 times the integral of sine of 5, I'll put an x in, squared dx from 0 to pi. And that gives me the area of the entire shape, 0.785. And then I know there are 5 petals because when there's an odd number, it's the same number of petals. So then I do 0.785 using more decimals from the calculator divided by 5, which gives me my final answer. Here, let me put this final answer of approximately 0.157. The other option, which is the one I prefer, is to find where it starts and stops. And a petal starts and stops at the origin, or where r equals 0. So we find where sine of 5 theta is equal to 0. And I don't need everyone. Of course, there are infinitely many points or infinitely many theta values for which sine of 5 theta is 0. I just need 2 consecutive ones. So I know that if sine of 5 theta equals 0, then 5 theta could be 0 because sine of 0 is 0. Or the next one will be at pi from our unit circle. So sine is 0 here, sine is 0 here. Now it does keep going on both ends, but these are consecutive. When I solve for theta, I get theta equals 0 or pi over 5. And so I can do this area, 1/2, integral from 0 to pi over 5 of sine squared 5 theta d theta. And assuming I did everything right, which is sometimes a good assumption, I should get the same answer I have right here, exactly. So 1/2 times the integral of sine of 5 theta all squared d theta from 0 to pi over 5. And lo and behold, I do get the same exact answer. Let's look at the graph. So this one looks like that. As you can see, there are 5 petals, and one petal starts at a theta of 0 and comes around, and the next time it hits the origin is at 5 pi. Sorry, pi over 5. One more thing to make sure is clear. You might be wondering, hold on, sometimes this petal was obtained by a positive r value, this was obtained by a negative r value. How does this area function make things stay positive? Because I should accumulate the area for each of these even when r is positive or when r is negative. And the answer to that is, since we have this squared, so I'll put that in 0.157. Since this is squared, it will make the negative r's positive anyway. Alright, I hope that helped out. Feel free to comment below with any questions.